Annenberg Media.
A body in uniform circular motion has both constant speed and constant acceleration. Uniform circular motion can describe the orbit of the moon.
I don't know who invented the wheel, but the circle was invented by primitive peoples all over the world. Usually it had some mystical significance. It was associated with the horizon, or with the sky, or with the gods. After a while, myths take on complicated traditions and fancy language, and then they become known as philosophy. The Greeks, of course, were not mystics. They were philosophers. They saw circles in the sky just like everybody else, but to them, they represented not some myth of creation, but geometry. They imagined a universe filled with spheres turning on their axes so that the motions we saw seemed to us to be circular motions. And so the philosopher Plato said, all motions in the heavens must be circular motions and uniform. And astronomers spent the next 2,000 years trying to show that he was right. Now, astronomy was a profession. It had a job to do. The job was to predict where each heavenly body would be found at any given time on any given night. These predictions were important because they were used for agriculture, for navigation, and above all in those days, for casting horoscopes. But in any case, anybody could look up at the sky and see if they were right. And remember, the ancients spent much more time looking at clear night skies than we do. So, using circular motions, they had to predict where things would be, and they had to be right. It wasn't easy. For the stars, it worked pretty well, because the stars seemed to move in circles around us. But there were other bodies up there, which the Greeks called planets, meaning wanderers. And for them, it didn't seem to work. For one thing, they didn't move across the sky at constant speed. For another thing, they didn't even move in the same direction across the sky. They would stop and turn around and go backwards sometimes. Furthermore, two of them, Mercury and Venus, always seemed to stay fairly close to the sun, whereas the others didn't. And finally, they didn't always have the same brightness, meaning they weren't always the same distance from the Earth. Nevertheless, Plato had said that all of those motions were due to uniform circular motions, and that's what the astronomers had to accomplish. And so they constructed a system that worked remarkably well. It was based not on circles around the Earth, but on circles around other circles. These were called epicycles. To understand that, we have to make a little circle of our own and go back to where we started.
Probably every ancient culture discovered the circle. Walking symbolic circles around it, Native Americans worshiped the sun. Hindus noted what appeared to be the circular motion of the heavens, as did the Quechua Indians of Peru, and early Japanese astronomers. Heavenly forms and formations became models for earthly structures, and some of the earliest buildings dating from 5000 BC in Mesopotamia have a circular ground plan. Even a primitive hand can inscribe circles, and while they can be expressed by the more sophisticated language of mathematics, the concept remains relatively simple. The vector from the center to each point on a circle always has the same length. This simplicity might have been part of its appeal. From simple ideas, magnificent structures grew. Images proliferated, were embellished upon and further elaborated. The circular form of ancient Stonehenge, for example. Humans imitated nature, and nature seemed to imitate them in return. Decoration became function, and function followed form. With the human touch, however, not everything was perfect in the nature of the circle. Sometimes it really is necessary to go back to the drawing board. The position of any point on a circle can be described by its Cartesian coordinates, or by its distance from the center and the angle to the x-axis. These descriptions are related by trigonometry. For just about anyone with a head for figures. The circle is a powerful symbol, organic to the universe, and most of the civilizations within it. In some cultures, not only the circular form of the heavens, but the heavenly circular motions are as manifest today as they were in ancient times. The Greek philosopher Plato declared the circle ideal and asserted that all other forms were imperfect, inferior representations. He decided circular motion describes the heavens, not merely circular motion, uniform circular motion. Each heavenly body was to be a point moving on a circle at a constant rate. Viewed another way, the vector is at an angle that grows at a constant rate. That rate, omega, is known as the angular speed of the object. So at any time t, the angle theta equals omega t. In one revolution, the object moves through 2 pi radians in time capital T. Therefore, the angular speed is 2 pi over capital T. Plato often said that God was in the habit of geometrizing. Perhaps that's why Plato's ideals of perfection and of a universe in harmony struck a responsive chord with scholars and mystics for centuries afterward. For Plato, the physical universe was bounded by a rotating sphere of fixed stars, centered on the stationary fixed Earth. Inside the sphere of fixed stars, traveling in circular paths with individual uniform motion, were 7 planets: the Moon, Venus, Mercury, the Sun, Mars, Jupiter, and Saturn in that order and extending outwards. Greek astronomers saw the planets as erratic bodies, so much so that the very word planet meant to wander, to mislead, or to deceive. Planets were deceitful because they refused to obey Plato's dictum of perfection, uniform circular motion. Nonetheless, this Platonic ideal was eventually accepted by Europe's noble thinkers. And why not? Didn't the ruling class and common folk alike have much in common with the planets themselves? Indeed, on any level is not human behavior like that of the planets, often erratic. And when certain conditions exist, don't humans, like the planets, tend to wander or appear to be deceitful? But in the Royal Renaissance, of course, neither planet nor noble person was subject to criticism for being less than perfect. Perhaps that's as it should be, because whether in the heavens or on earth, erratic behavior doesn't necessarily mean imperfection. Perfection, after all, is in the eye of the beholder, and so is reality itself. So even in this, the best of all possible worlds, can the naked eye see reality perfectly? Not always. Sometimes perceptions of reality may be mere shadows of the real thing. Something that seems to have its ups and downs, for example, may in fact be going around in circles. And in the language of vectors, the shadow of a motion may be only one of its components. Circular motion actually has two separate components. The original vector is the sum of these. And that's why circular motion can be described by a vector equation. But the motions of the planets, as seen against the background of the stars, were much more complicated. Because they seem to contradict the idea of uniform circular motion, theoretical models of planetary motions were created by Plato's followers. Each one attempted to save the appearances, in other words, to make observed behavior compatible with the Platonic ideal. One attempt, an invention by Apollonius of Perga, was called the epicycle. The planets moved on small circles attached to a larger circle, which was also turning. The large circle was called the deferent, and the smaller one, the epicycle. In the hands of a skilled mathematician, this combination of circular motions can produce many forms. For example, viewed from the center of the deferent, that is the Earth, the planet seems to behave strangely. If the deferent and epicycle rotate at the same speed, however, the figure is just another circle whose center is offset from the Earth. On the other hand, if the epicycle rotates exactly twice as fast as the deferent, the result is another smooth curve, an ellipse. The ellipse would later be recognized as the actual shape of a planet's orbit around the sun. Apollonius wrote a celebrated treatise on curves, one of which, ironically, was the ellipse. But ancient astronomy reached its highest point 400 years later in the Roman colony of Alexandria, the Queen City of Egypt. In that fabled city lived Claudius Ptolemy. Among many accomplishments, he compiled the Almagest, an encyclopedia that summarized 5 centuries of Greek science into 13 extraordinary volumes. Ptolemy was not above abandoning Platonic theories of perfection, and in fact, he added a few twists of his own. For example, the deference of the superior planets, Mars, Jupiter, and Saturn, did not rotate at uniform rates about their centers, and he adopted an oval orbit for Mercury. As startling as Ptolemy's variations were, they were lost like esoteric footnotes in the sheer mass of the Almagest. And of course, they were also overwhelmed by that overriding principle of the Greek astronomers, a system based totally on uniform circular motion. Ptolemy's variations on Plato's theme of perfection were comparatively subtle, but they had a profound effect on Nicholas Copernicus. Wanting to reform the Almagest, Copernicus put the sun at the center of the solar system, and by using epicycles liberally, he managed to save appearances. In spite of the epicycles, Copernicus's universe had planets going around the sun and the moon going around the Earth in very nearly uniform circular motion. To maintain traditional aesthetic preferences, he created a newer and more accurate vision of the solar system, the Copernican system. A century and a half later, Isaac Newton revealed why it worked, starting with his theory of the moon. The moon is always falling, yet it stays in the sky. The gravitational force from the Earth makes the moon accelerate according to F equals ma. Although it continues to accelerate all of the time, it moves at nearly constant speed. This seems to contradict the very concept of acceleration. But acceleration is the rate of change of velocity, and velocity is a vector. The speed is only its length. A body can be accelerated even if its speed is constant, provided its direction changes. This point becomes clearer with the introduction of another concept, the derivative of a vector. The derivative of a function explains how fast it's changing at any given instant. The derivative of a vector explains how fast the vector is changing. A vector can change by changing its size, or its direction, or both. The change in a vector is itself a vector. The vector, v, although it's always perpendicular to r, is itself undergoing uniform circular motion. Its derivative is the acceleration. That solves the puzzle of constant acceleration at constant speed. As a body undergoes uniform circular motion, the acceleration continually redirects the velocity vector, which continually redirects the radius vector. They all keep in step with each other, constant in magnitude, but changing continually in direction. The idea of the derivative of a vector is not as new as it may seem. Remember, F equals ma is itself an equation about the derivatives of vectors. The only difference is that previously, by taking derivatives one component at a time, only ordinary functions have been differentiated.
In uniform circular motion, the velocity is perpendicular to the radius vector, and the acceleration is perpendicular to the velocity vector. So it points along the radius vector, but in the opposite direction. But how big are the vectors? V is equal to omega r, and A is equal to omega V. So A is equal to V squared over R.
Those are the relationships among radius, velocity, and acceleration, locked together in the eternal dance of uniform circular motion. Isaac Newton understood that any body that moves in uniform circular motion is being accelerated all of the time. He called this centripetal acceleration. According to Newton's second law, a force is required to produce that continuous acceleration. For a body in orbit, that force is gravity. The length of the radius vector determines the gravitational force. This force, then, determines the acceleration. But circular motion requires this relation among radius, speed, and acceleration. So, if a body starts out with just the right velocity, its speed stays constant, and uniform circular motion results. Newton's theories are essentially mathematical in nature, and much has been made of their mathematical character. But what's to be made of the nature and character of Newton himself? Newton scholars frequently characterize him as acutely suspicious and jealous, often without cause and nearly always to a fault. Solitary, ill-tempered, vindictive. Considering those traits, only the most creative fiction could portray Sir Isaac Newton as a jolly fellow. His mercurial disposition hardly made him a victor in contests of personality. Toward his contemporaries, he had no peers. He was cool, if not antisocial, and history is almost blank with accounts of Sir Isaac's laughter.
Is it? Well, I'm not warm.
Have your robe, sir?
Yes, please. What's for breakfast?
Guess your favorite, sir.
Ah.
Newton's general disdain for the intellectual achievement of his colleagues, to say nothing of the mundane, makes his election to Parliament seem all the more surprising. Yet Newton was not without the great friend, nor the odd moment of levity. And his personality, like his evaluation of Copernicus and Aristotle, is more properly seen as a study in contrasts. Besides, the essential issue in the mechanical universe is not what motivated Newton the man, but what Newton revealed as a scientist. And regarding his revelations about the workings of the moon, the facts are clear. It's a long way from the Lincolnshire farm that nourished Newton's fertile imagination. Longer still from the mysticism that drove the primitives to question the heavens. A long way, along a circular path from the past to the present and into the future.
Now, in the interest of justice, I want to change the subject completely. One of the most heinous activities that governments engage in is the torture of prisoners. Today, so far as I know, no government anywhere in the world openly admits to torturing prisoners. But of course, we all know that they do it secretly and illegally. In earlier times, however, that is in medieval times, right up through the Renaissance, torture was an open legal practice. That meant that thumb screws, racks, stakes in flames, horses that pull the body in various different directions at the same time, all of those were instruments of government policy. But the fact that it was a legal institution had compensations even for the victims. For one thing, it meant that the executioners were skilled professionals. In other words, for an appropriate bribe, they could put on a pretty good show without causing too much pain. Usually that was done by making sure that you were past caring before the exciting part came. More importantly, the fact that it was a legal institution meant that it was subject to laws and safeguards. They didn't just hustle some guy into a back room and start beating him up as they might do today. Before physical torture could take place, a panel of judges had to meet and deliberate on the merits of the case and decide how far the process could go. There were actually two stages that had to be gone through before actual physical torture. The first was the mere threat, the verbal threat of torture. If you remember, in the trial of Galileo, that was all that was ever authorized. But in Galileo's case, that was enough. The next stage was called showing the instruments. That is, the prisoner would be taken into the room and shown the actual instruments of torture. It was a very impressive sight, and it almost always had the desired effect. You may be wondering why I'm lecturing to you on such a bizarre subject. Well, the purpose is to introduce our next topic, which is about the use of force. I'll see you then.
In uniform circular motion, the velocity vector is perpendicular to the radius vector, and the acceleration is inward along the radius. According to Newton's second law, any body that executes uniform circular motion is being accelerated by some external force. For a body in orbit, that force is gravity.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.